Many people have asked kind of the same question. What is the innovation? What's the future? What's the new technology in food packaging? And scientists have answered the question with two words, the smart packaging. I'm honest with you, I heard the terminology around 15 years ago. But still, smart packaging is ongoing. But some people describe it using like opposite terminology, like a dumb packaging. I'm honest with you again, I don't like this terminology. It may make people think traditional packaging is dumb. But traditional packaging is still doing good job so far, so there is no problem. But maybe we may need to describe it in different way. The traditional packaging may be traditional and passive and one dimension, like a protection, containment, and transportation. But smart packaging is doing something extra, such as it is carrying information or it is providing some special multi-dimensional activity. That is the definition of smart packaging, which I'm teaching at Virginia Tech. So, and smart packaging is grouped with two main categories. One is active packaging. The other one is intelligent packaging. There are big differences between smart active packaging and intelligent packaging. Food and packaging, they are interacting to each other. Active packaging means the packaging material is providing extra activities such as antimicrobial activity or removing some gases like oxygen or the ethylene gas. But intelligent packaging, again, is carrying information and it makes a manufacturer or a customer decide their decision whether or not they'll buy it, or it has some information for like an entire life cycle things. There is a big difference between intelligent packaging and active packaging. So what is driving this trend in food packaging? Probably demand from the society. It includes the sustainability and cultural diversity and traceability and health and safety issues. And also, the existing manufacturing process might have some limitation, then they need some improvement. And it may relate it to direct economies and also the marketing purpose. Top three things are summarizing the driving forces, but I want to summarize what I mentioned above. The smart packaging means we need better functionality and better safety. That's the reason why our food packaging scientists are trying to develop new technologies. And market-wise, smart packaging is growing. 2015, I just read the internet a few days ago. 2015, the smart packaging market size around $29 billion size. But based on the market report, 2020, the market size will be around $40 billion size. In general, packaging, the growth rate annually is 3.8, lower than 4 point. But smart packaging is higher than that of the packaging industry growth. So it means society needs smart packaging or innovation more. Active packaging, it includes many different areas. It may release something, or it may remove something. It may control the temperature, or microbial contamination and quality control, quality things. Let's skip this one. One of active packaging include the successful active packaging is oxygen scavenging system. Oxygen scavenging system may have two different functions. One is the active agent, like oxygen scavenger, maybe in the film or container in the matrix, then improve oxygen barrier property. The other way, oxygen scavenger is used for removing residual oxygen from headspace. There are two different the ways. Like this, while you are driving on the highway, you may stop by a gas station, then buy beef jerky, then you open it, then you can see small bag inside. Small bag is not simple moisture absorber. It is one of active packaging called oxygen scavenger. It is removing residual oxygen from the bag and keep beef jerky the fresh. Especially beef jerky, why they are using oxygen scavenger in the inside? Because beef jerky is very sensitive to oxidation. It contains tons of lipid and fat. Then those are very sensitive to oxidation. Then packaging engineer, they have to put oxygen scavenger there can improve the shelf life. Another way, you have seen the plastic beer bottle. Plastic beer bottle definitely made out of multiple layer structure, 7 layer structures. One of them may be nylon or the EVOH. EVOH and nylon, those are used for oxygen barrier property. But still, we need better oxygen barrier property than like a nylon and EVOH. Then they add oxygen scavenger in the glue layer, tie layer, or some other layer. Then entire oxygen barrier property is improved. So that's the way to use the oxygen scavenger in food packaging. And another successful active packaging is MAP, modified atmosphere packaging. Most produce, agricultural products, they are still alive. But for example, apple, when is the harvest time? Maybe October, September, late September or November, right? But you can buy apple all seasons, like May and June, July. If you go to grocery, then you can buy apple. How? How is it possible? Packaging engineer, they are controlling the air composition. Like they are controlling the composition of carbon dioxide and oxygen in the room. Then breathing rate of apple or banana or any produce, it changes. Ripening process is changing. Then you can buy, customer can produce an agricultural product anytime. It's a good success of active packaging. And also, like a cooked MAP is also used for pre-cooked or processed food very often. It can control microbial contamination and the oxidation process as well. For MAP, many different gases can be used. Basically, we are controlling oxygen, carbon dioxide, and nitrogen, but also we may add CO gas or SO2 gas or the other inert gas. Then the entire functionality is changing based on the composition of air. Good example. Actually, I copied this table from the textbook, but I forgot the textbook. That's the reason why it doesn't have any information about that. This table here. If you look at, I don't know whether or not you can read it. Before and after using MAP, like fresh red meat, without MAP, it may last 2 or 3 days. But after using MAP, it is okay, around a week. And also, the fresh, the pasta, without MAP, maybe it'll last 3 days, but after applying MAP, it'll last more than 2 months. That's the big success of active packaging. So we are now using this active packaging for the real food product. And also, I like this picture. I'm using this picture for my class all the time. I call it, if you go to grocery and buy a bag of coffee, then there is looks like belly button. Have you ever seen like a button? Yeah, looks like a belly button. I call it belly button, but official name is one-way gas valve. What's the characteristics of coffee? Aroma, right? That's the indicator of the freshness. So this belly button, one-way gas valve, is controlling carbon dioxide, the concentration and aroma concentration in the bag. Then controlling entire pressure. Then it will keep the coffee granule the fresh. That's the purpose of this new device here. Maybe you'll be surprised. How much? Do you know how much it is? It must be very expensive, but it's 1 cent. It's very cheap. Then it's applicable for a real product. So then not only like this is the Starbucks, but maybe it's the Dunkin' Donuts, I guess. I like Dunkin' Donuts and Starbucks both. So anyway, this one, Dunkin' Donuts and Starbucks, they are using this one-way gas valve a lot. So you can buy and try to open it, and you can see this valve. And another example of active packaging, maybe antimicrobial packaging. I'm honest with you, a lot of scientists are working on this area, but I couldn't see real successful stories so far. Some applications are existing, but I don't see like a big success in antimicrobial packaging. But we need it, so many scientists are working on this area. Because food is related to, food is a good source for bacteria. Then once pathogenic bacteria is there, then people may be sick. So we have to prevent that incident. So then packaging engineer try to develop new system called antimicrobial packaging. And packaging itself prevent microbial contamination, typically pathogenic bacterial contamination. There are different ways. Again, packaging material like this, entire packaging material may be antimicrobial the things. And packaging, like existing packaging material, may be coated with antimicrobial agent. And the food is directly contact to the package. And sometimes we add some small bags or sachet inside, then those are interacting with the food, then antimicrobial activity is the control. But again, these are ideal the ways, but so far again there is no such a big success which people public people can recognize. The reason why is not really not successful is comparability in terms of processability. It is not really okay with plastic manufacturing process. Plastic manufacturing process means we are heating it up to maybe 150 degrees Celsius or 200 degrees Celsius, something like that. But most antimicrobial agents, they are not stable at the temperature. So it means manual coating or room temperature coating must be applied. Then feasibility for mass production is a big problem. That's the reason why there is a big hurdle so far to use antimicrobial packaging in current the food the system. Another category of the smart packaging again is intelligent packaging. Intelligent packaging is designed for example, tamper evidence and product integrity and the safety quality indicator and freshness indicator as well, and traceability and authenticity. We are using some typical device or material to do these the function. Successful intelligent packaging example may be RFID. RFID is applied at a lot of expensive the product, not only food, also the electrical device has RFID in the package, and also pallet is equipped with RFID. Then the manufacturer can see where their pallet is located, then they can track down entire the history of transportation. That's the goal of intelligent packaging. And I like this slide to, which is connected to the intelligent packaging, because traceability is the one of a hot topic in the world. So traceability needs some special smart packaging system called intelligent packaging. So in general, the traceability in food, we are focusing on traceability because to prevent something bad to public health, to us. Sometimes, for just in case, sometimes product is contaminated by salmonella or listeria or something really bad, then government or company or customer must know where it's stuck and how to collect them. Then traceability is getting important because it's directly related to our health. You may remember 2009, there is a big the record that, about like a peanut-related product, right? A lot of people were sick because of the peanut. Peanut was contaminated by salmonella. So at that point, we didn't think about packaging engineer. We didn't think about traceability at all. But not only this record, historically, we had a lot of the problem in the food product. Then scientists and government and the customer, hey, we need to have a system to track down our product and easy to collect, easy to fix the problem. That is the starting point of traceability in food packaging. So food packaging, in food packaging, again, there are many ways to incorporate intelligent packaging concept. One of them will be RFID. RFID is equipped in the product, then it is carrying all information. The other way is, actually I like this slide because I have worked with one company around 8 years ago. Then I don't know whether or not you are familiar with Gaia Earth. They are the manufacturing organic the food supplement. Like 8 years ago, we thought, hey, we want to provide some information about product to customer. Then they put the number here, like a tracking number here at each product. Then customer can use this number to see entire history of the product. It's a good example of traceability. Then it is really successful. They have very strong the customer who is showing good loyalty because they are doing something new for their customer and for their product. So again, this slide is showing some example of traceability for the nutraceutical product. And even that website is carrying the information about where it is harvested and where is the process. And now, so we discussed about some the new technology, and also in the future we are heading to some a new material area, because existing material has some problem, like a plastic. People believe, it's not true. It's not sustainable. I believe plastic is more sustainable than other materials, but people believe we may look at we may need to look at other materials. Other material may include bioplastics. So bioplastic, to use bioplastic, oh, looks fancy. It's biodegradable and compostable. Wow, it's good for marketing. But problem of bioplastic is not providing good functionality comparing to traditional plastic packaging material. Then we have to improve the functionality of bioplastics and biopolymer. So scientists like me, we are investigating the effect of nanomaterials. I mean, we are still using nanomaterials for existing the plastic, but nanomaterial composite with bioplastic, maybe it gives more benefit. So nanomaterial is used for some strength or gas barrier property. But still, nanomaterial, as you heard in the morning, there is a lots of limitations like safety and cost and processability and feasibility for mass production. But still, we are working on that. Nanomaterial in packaging, maybe clays, a lot of different types of clay, hydrophilic clays and hydrophobic clays. And sometimes, nano size titanium dioxide. Actually, I'm working on that area. And some carbon-based material, like a carbon nanotube and carbon fiber or graphene or graphite-related material. Those are potentially useful in the food packaging. And also, nanocellulose gel or nanocellulose crystals. Those are receiving lots of attention from scientists and also the manufacturers because it is providing good functionality comparing to carbon-based material. So now I'm introducing the ongoing research project at Virginia Tech. We have a good material scientist at Virginia Tech. We are working on several different topics. One of them will be one of them is making the replacement for polystyrene foam. We used nanocellulose gel, then used different manufacturing process, then see whether or not it can replace existing polystyrene foam. Then we found, the good the potential using in use of nanocellulose. So look at this. One of the students made really good foam using nanocellulose gel. Actually, this project is related to U.S. Army. U.S. Army wants to replace polystyrene foam for their like heavy weight the weapon. And also, one of the topic at Virginia Tech is, a lot of convenient food is not really sustainable because they once they are used by customers, then they are going to landfill without like a separation. Like a K-cup is a good example. K-cup and coffee granule, used coffee granule. Nobody dump out coffee granule from the container, then separate plastic container for recycling, right? 1/3 the family in the United States, they have the Keurig machine at home. It means every day, like millions of cups are used. Millions and millions of cups are used, and they are going to landfill area. It's a big the social problem. So our scientist team, actually my graduate student and other faculty members, graduate students, are working on developing the biodegradable. Once customer throw it away, then it will be degraded with coffee granule together. So we don't have to worry about the recycling the problem because product characteristics, we can't separate coffee from the container. It must go to trash can, then it must be degraded, right? That's one of the area what we are doing at Virginia Tech. And the other one is we are also modifying titanium dioxide, surface modification. Done, almost done. So TiO2 is used everywhere in the packaging product. So problem of TiO2 is, it is carrying white color. Sometimes it is good, but some packaging material doesn't need white color. Transparency is required. So we change the surface using some fatty acid. And look at this. I don't know whether or not you can see it. After modification, this one is modification in chloroform. After the surface modification using a fatty acid, the titanium dioxide, which is highly hydrophilic material is not mixed with hydrophobic material, but now is well mixed with chloroform and toluene. So then after we apply this modified titanium dioxide in the package, then packaging material is going to be transparent, not pure white color anymore. And also it has additional functionality based on titanium dioxide. And also one of my research team is working on using carbon materials. Carbon nanotube or graphene oxide or graphene or carbon fiber have been used in many industries. But in packaging, it is not used because of price. Those are really expensive. So we are trying to find some alternative way to reduce the price. So we found some like carbon material conjugated with the biopolymer or the other carbon-based material can improve all functionalities, including gas barrier properties. So that's what we are doing at this at Virginia Tech. And this is the old project. Also, we are improving thermal stability and gas barrier property of bioplastic using inclusion complex technology. This is the PLA, polylactic acid, and this is the beta-CD, and it formed inclusion complex. I have patent, and one company is using this technology right now, and it's completely different from the simple mixture. Then it improved thermal stability from 50 degrees Celsius. That's the thermal stability of PLA up to 70 degrees Celsius. So that's the huge improvement. And look at this. After incorporating inclusion complex, then PLA bottle is okay at high temperature oven for long term, comparing to pure PLA and comparing to even regular PET. Conclusion: smart packaging will grow because multi-dimensional the functionality. Those are related to like a new paradigm, which our world is demanding, like traceability and security and sustainability. And also, innovation in packaging material is more related to, in the future, more related to the sustainability and some kind of nano technology. That's what scientists are expecting for future in the food packaging area. Thank you.